Welcome to my channel, Cosmic Lullaby Channel, where relaxing stories and fascinating facts come together to help you unwind and fall asleep peacefully. Night falls, and across the globe, humanity looks to the sky, a portrait of peace, of tranquil eternity. But this is a deceptive peace. Tonight, we pull back the veil on that silence to expose a covert, high-stakes conflict that has raged for 13 billion years. This is not a war of nations, but a cosmic struggle for dominance, for resources, and for the very future of existence. At the heart of this battle, the stars themselves. They are not merely distant points of light. They are colossal nuclear reactors, economic powerhouses forging the very elements that make up our bodies, our world, and everything we know. Every twinkle of light is a message from the past, a time-delayed intelligence report. The starlight reaching our eyes tonight may have left its source hundreds, thousands, or even millions of years ago. To strategic analysts of the cosmos, this means we are observing history. Some of those stellar powers may already be gone, their light the final ghostly whisper of a dominion that once was. Others, the enduring empires, will continue to shine long after our world has passed. In this cosmic arena, scale is a form of absolute power. Consider the case of Scooty, a red hypergiant. Our intelligence models identify it as an unstable hegemon. With a radius more than 1,700 times that of our Sun, its sheer scale defies imagination. If placed at the center of our solar system, its outer surface would extend beyond the orbit of Jupiter. Earth would be nothing more than a vaporized speck, incinerated deep within its churning, incandescent atmosphere. Even smaller supergiants like Betelgeuse or VY Canis Majoris would completely engulf the orbit of Earth. But this extreme power comes at a steep strategic cost. These massive stars are exceptionally rare, operating on a high-risk, high-reward timeline. They burn through their fuel reserves with reckless abandon, and their lifespans measure in mere millions of years, a flash in the pan compared to the billions of years of stability enjoyed by ordinary stars like our Sun. Their swollen atmospheres are a physical manifestation of inherent instability. They constantly hemorrhage material into space in great billowing clouds, like an empire unable to control the leaking of its own vital resources. The sheer size of these giants forces a critical reassessment of our own position. Our Sun, though immense by everyday standards, is revealed to be a modest middle-power nation on the galactic stage. Its existence is a testament to a strategy of long-term stability over short-term violent domination. While some stars dominate through sheer physical presence, others wield a different weapon: pure, unadulterated energy. There exist rare titans, luminous blue variable stars like Eta Carina, that release so much energy they can rival the combined light of entire small galaxies. They are the energy tycoons of the universe, capable of outshining billions of competitors. In the 19th century, Eta Carina underwent a violent eruptive event, a sudden, shocking display of power that briefly made it the second brightest star in the night sky. This was astonishing, given that it lies more than 7,000 light-years away. That eruption was a geopolitical shockwave, a declaration that even from an immense distance, a single entity could rewrite the apparent balance of power. Stars of this type live dangerously, consuming their hydrogen at astonishing rates and often ending their reigns in cataclysmic supernova explosions. Their immense light pushes outward so forcefully that it blows away their outer layers in powerful winds, creating glowing nebulae that surround them like an emblem of their wealth and influence. These beacons of brilliance are a stark reminder that for a brief time, a single star can utterly dominate the cosmos around it. The life cycle of the most powerful stellar empires is one of spectacular rise and catastrophic fall. When a massive star exhausts its nuclear fuel, the outward pressure from fusion ceases. Gravity, the relentless force of collapse, wins its final victory. The result is a supernova, the most violent event in the known universe, a state's complete and utter implosion. But this is not an end, it is a transformation. From the ashes of a fallen superpower, a new and bizarre entity can emerge. The core of the dead star, crushed under its own unimaginable weight, may survive the blast as a neutron star. These objects are strategic paradoxes. They are ghosts, the collapsed remnants of once great suns, yet they possess a power density that defies comprehension. A neutron star is typically only about 20 kilometers wide, the size of a city, yet it contains more mass than our entire sun. The collapse is so extreme that it squeezes atoms together, forcing protons and electrons to merge into neutrons, creating a form of matter denser than anything known outside of a black hole. The economic implications of this are staggering. A single teaspoon of neutron star material would weigh billions of tons on Earth. It represents the ultimate concentration of assets, a vault of matter so dense that its value is nearly infinite. Their surfaces are solid, their gravity is immense, and their influence, though subtle compared to their former selves, is profound. These stellar remnants serve as a warning about the fundamental understanding of matter and serve as a warning about the extremes to which physics can be pushed in the wake of a collapse. Among these stellar remnants, some evolve into highly specialized actors. These are the pulsars, and they represent the emergence of order from chaos. A pulsar is a neutron star that rotates at breathtaking speeds, often hundreds of times per second, faster than the blades of a household blender. With each spin, it sweeps powerful beams of radio waves or light across the cosmos. And from our vantage point on Earth, this creates a pulse of remarkable regularity. These pulses are so precise, so metronomically perfect, that astronomers use them as cosmic clocks, capable of keeping time with greater accuracy than our best atomic standards. When they were first discovered in the late 1960s, their clockwork signal was so unnatural, so seemingly intelligent, that it sparked immediate speculation they could be beacons from an extraterrestrial civilization. The truth was, in some ways, even more profound. These were not signals of life, but of a physical order so extreme it mimicked intelligence. Today, pulsars are among the most valuable strategic assets for cosmic intelligence. They are used to test the predictions of Einstein's theory of general relativity with unprecedented accuracy, and even to hunt for gravitational waves, the faint ripples in space-time itself. They are the most reliable lighthouses in the cosmos, their predictable signals providing a grid of timing and navigation across the galaxy. But if the pulsar represents order, then another outcome of stellar collapse represents pure, unadulterated terror. These are the magnetars, an exotic and fortunately rare type of neutron star. They are defined by their magnetic fields, the strongest known to exist in the universe. A magnetar's field can be 1,000 trillion times stronger than Earth's, a figure so large it is almost meaningless. This is not a force that merely attracts or repels. It is a weapon of fundamental destruction. A field this powerful would be sufficient to distort atomic structures, tearing apart molecules and rearranging the very fabric of matter itself. When these colossal magnetic fields suddenly shift and reconfigure, an event known as a starquake, the magnetar can unleash a giant flare, releasing more energy in a fraction of a second than our sun will emit in hundreds of thousands of years. These bursts of gamma rays are so powerful, they have been detected across vast galactic distances, briefly outshining every other star in our galaxy combined. A magnetar is the cosmic equivalent of a rogue state armed with a doomsday weapon. They are extreme laboratories in space, demonstrating what happens when the laws of physics are pushed past every conceivable limit we can replicate on Earth. The death of a single massive star, therefore, does not lead to a power vacuum. It creates a new strategic landscape populated by dense remnants, precise information brokers, and unpredictable, overwhelmingly powerful rogue actors. The strategic landscape of the cosmos is not only defined by birth and death, but by the myriad instabilities that plague a star during its operational lifespan. Not all stars are perfect spheres, the idealized models of stability. Some are compromised by powerful internal forces. When a star rotates with extreme velocity, centrifugal force begins to overwhelm its own gravity. The star's equator bulges outward, flattening it into an oblate, squashed shape. This is a celestial body under immense internal stress. One key case study is Achernar, a star spinning so rapidly that its equatorial diameter is a full 50% larger than its polar diameter. From a strategic perspective, this is a nation whose internal economic or political velocity is so high that it risks tearing itself apart from the inside. This rapid rotation is not without consequences. It can fling material into space, forming vast disks of gas that orbit the star. This is the cosmic equivalent of capital flight, a constant low-level bleeding of resources caused by an unsustainable internal policy. These distorted suns challenge the simplistic image of stars as balanced, stable entities. Instead, they reveal a more turbulent reality, where a star's life is dictated not just by its mass, but by the violent dynamics of its own spin. There is a strategic trade-off at play. Some models suggest this rapid rotation may mix the star's internal layers more effectively, prolonging its fuel supply and extending its lifespan. It is a high-risk, high-reward strategy, a gamble that the benefits of increased efficiency will outweigh the constant risk of catastrophic structural failure. While some stars contend with internal pressures, others buckle under the weight of their own immense scale. The hypergiants are the most unstable and short-lived empires in the universe. Their colossal size comes at a crippling cost. They burn through their fuel reserves with such ferocity that their own gravity cannot maintain control over their outer layers. The result is a state of perpetual decline, a hyperinflationary collapse on a stellar scale. They shed mass through powerful stellar winds at a rate that is difficult to comprehend, losing the equivalent of our sun's entire mass in just a few thousand years. This is not a slow, managed decline. It is a frantic, uncontrolled liquidation of core assets. The overall mood of the famous hypergiant Eta Carinae is a prime example, surrounded by a vast nebula, a glittering monument to the material it has violently blasted into space. This process, while utterly destructive for the hypergiant itself, is a vital part of the galactic economy. These storms of gas and dust enrich the surrounding interstellar medium with heavy elements, the raw materials required to form new stars and planets. It is a form of creative destruction. The collapse of one great power seeds the rise of countless smaller ones. The hypergiant's fate is all but certain: a violent explosion as a supernova, perhaps leaving behind the ultimate collapsed state, a black hole. They are cosmic firestorms, magnificent and self-destructive, a testament to the fact that being the biggest power in the region often means you are also the most vulnerable. But the greatest threat to a star is not always internal. In the cosmic ecosystem, there are predators. And there is no predator more absolute than a supermassive black hole. A star that ventures too close to one of these gravitational hegemons faces a violent and certain end. The black hole's tidal forces, the difference in gravitational pull between the near and far sides of the star, stretch it like taffy in a process of brutal, overwhelming subjugation. If the star strays inside a critical boundary, it is torn apart in a cataclysm known as a tidal disruption event. This is not a merger or a battle, it is a hostile takeover, an annexation. The stellar material, the assets of the now liquidated star, is pulled into a spiraling, glowing disk as it falls into the black hole. The overall mood, the friction within this disk heats the material to millions of degrees, releasing a burst of light that can briefly outshine the combined light of an entire host galaxy. This flare is the public announcement of the conquest, a broadcast of destruction across the universe. For our intelligence agencies, these rare events provide a unique opportunity to study the otherwise invisible black holes that lurk at the centers of galaxies. Each tidal disruption event is a cosmic drama, the brilliant death of a star shredded by the ultimate, indisputable force of gravity. When our observational outposts detect a sudden, intense flare of light from the center of a distant galaxy, our analysts understand they may be witnessing the final moments of a star. These are the telltale signatures of a tidal disruption event, the brilliant death cry of a sun being consumed by a supermassive black hole. The process is a strategic analyst's goldmine. As the star is shredded, its material forms an accretion disk, a swirling vortex of gas heated to millions of degrees, shining intensely in X-rays and ultraviolet light. This flare, which can last for months or even years, is a detailed report on the transaction. By studying its light curve, how it brightens and fades, and its spectral data, we can deduce critical intelligence about the aggressor. We can measure the mass of the black hole, understand its feeding patterns, and gain insight into the dynamics of galactic cores. The destroyed star becomes an unwilling informant, its violent end illuminating the nature of the dark power that consumed it. These events are a powerful reminder that even entities as immense and radiant as stars are not safe from the deeper, more fundamental forces that shape the universe. A natural Mel narrator is to glimpse the raw, consuming hunger of gravity itself. But not all high-energy events are acts of consumption. Some are acts of creation. When two stellar remnants in a close binary system, particularly two neutron stars, finally spiral together, their collision is one of the most productive events in the cosmic economy. This is not a takeover, but a merger of titans, two of the densest objects in the universe combining their assets. The merger releases energy not only as a spectacular burst of light, but as ripples in the very fabric of space-time, gravitational waves. These waves, predicted by Einstein, travel outward at the speed of light, stretching and squeezing the universe as they go. In 2017, humanity's instruments achieved a landmark intelligence breakthrough. For the first time, we detected both the gravitational waves from such a collision and, moments later, the associated bursts of gamma rays and visible light. This was the birth of multi-messenger astronomy, the equivalent of confirming satellite intelligence with ground-based sources. We could finally see both the fundamental market shockwave and the public announcement from the same event. But the most significant outcome of this merger is industrial. These collisions are the primary forges for many of the heaviest elements in the universe, including gold and platinum. They are the universe's precious metals factories, seeding the cosmos with the materials that will later form planets and, perhaps, underpin the economies of future life. Every ring of gravitational waves we detect is a signal from a high-stakes merger, creating immense value in a location unimaginably far away. The same gravitational chaos that can merge stars or destroy them can also lead to another, stranger fate. Not every star remains safely within the borders of its home galaxy. The overall mood of the cosmos must have been some flung outward at such high speeds that they escape galactic gravity entirely, destined to drift alone through the vast, empty darkness of intergalactic space. These rogue stars are the political refugees of the cosmos. They can be launched by violent events, such as a close gravitational encounter with a supermassive black hole that acts as a powerful slingshot, or during the chaotic breakup of a dense star cluster where gravitational dynamics eject members at high velocity. Once ejected, they wander the cosmic void, carrying their planets, if any survived the ordeal, into an unimaginable and permanent isolation. Imagine a lone sun, billions of years from its birthplace, traveling endlessly with no galaxy to call home. Though difficult to detect, our analysts believe there could be countless intergalactic stars, scattered like embers blown from a great fire. They are a stark reminder that the universe is not static, but is filled with motion and chance, and that even something as massive as a star can be cast adrift on the cosmic sea, its citizenship revoked by the unforgiving laws of gravity. To comprehend the current strategic balance of the cosmos, we must look back to its origins, to an era before the great galactic empires, before the first planets, before even the raw materials for life existed. In the early universe, the economy was profoundly simple, composed almost entirely of hydrogen and helium. From this primitive state, the very first stars were born. Our intelligence refers to them as population 3 stars, and they were titans of a scale we can no longer observe directly. Our models suggest they were enormous, some hundreds of times more massive than our Sun. Formed from pristine gas clouds lacking the heavy elements that facilitate cooling, these giants grew rapidly and burned with a ferocious, almost desperate intensity. Their lifespans were strategically brief, perhaps only a few million years, a footnote in the cosmic timeline. But their purpose was singular and transformative. They were the first generation of cosmic industrialists, and their mission was to create the universe's first cache of heavy assets. When they died, they exploded in colossal supernova, and in doing so, they seeded the universe with the first carbon, the first oxygen, and the first iron. These were not just deaths, they were the universe's first acts of capitalization, scattering the foundational building blocks for all future economic activity, the materials required for planets, complexity, and life. None of these primordial stars survive today, but their fingerprints remain, embedded in the chemical patterns of the most ancient stars we can find. Studying these clues is like cosmic archaeology, allowing our scientists to piece together the story of how the first light pierced the darkness, transforming the universe from an empty hydrogen-based economy into a place capable of creating value. Just as there was a first generation, there will inevitably be a last. The fate of stars like our Sun provides a chilling forecast of the long-term economic future. When they reach the end of their lives, they shed their outer layers and leave behind a hot, dense core, a white dwarf. This is a retired economy. It no longer generates new energy through fusion, but glows with the leftover heat of its past productivity, like an empire living off its dwindling treasury. Over billions and then trillions of years, these remnants will slowly radiate away that residual energy, their light fading into darkness like a forgotten memory. The overall final stage is a black dwarf, a cold, dead star that no longer emits any discernible light or heat. It is a completely defunct asset, a company long since bankrupt. The most critical piece of intelligence here is that no black dwarfs yet exist. The universe itself, at 13.8 billion years old, is not yet old enough for even the most ancient white dwarfs to have cooled completely. The concept of black dwarfs belongs to the far future, a forecast of a time when the cosmos will be a quieter, darker, and profoundly poorer place. They represent the ultimate destiny of countless suns, a silent testimony that even the most radiant economic powerhouses eventually surrender to the inexorable laws of entropy and time. This forecast for individual stars scales up to a vision for the entire universe. If the cosmos continues to expand indefinitely, as current data suggests, its distant future will be a long, slow descent into total economic stagnation, a scenario analysts refer to as the heat death. In this future, the fuel for new star formation will be exhausted. The great stellar factories will shut down. The red dwarfs, the smallest and most efficient stars, will continue to burn for trillions of years, the last vestiges of a once vibrant economy. But even they will eventually fade, their light extinguished one by one. Galaxies will grow dim, their spiral arms dark and empty. Planets will freeze. The night sky will be a void. In this vision, the cosmos becomes cold and silent, populated only by the derelict remains of dead stars, black dwarfs, neutron stars, and the gravitational monopolies of black holes. Though this future lies unimaginably far away, the thought is both humbling and clarifying. The story of the stars has a beginning and an end. And we are alive at a privileged moment, a golden age when the sky is still bright with the light of cosmic industry. To gaze upward now is to witness a universe still in its vibrant, star-filled youth, a booming economy of light and creation. The forecast of a final universal heat death, while supported by current data, represents the end of our strategic timeline. But some theoretical models suggest that this is not the end of the story, but merely the end of a chapter. Highly speculative but compelling ideas from the frontiers of cosmology propose that our cosmos might be part of a grander cycle. Theories of a big bounce or the birth of new universes from the quantum substrate suggest that the final silence may be followed by a new dawn. In these fresh beginnings, the cycle of star formation could ignite once more. This is the ultimate post-collapse reconstruction scenario. The elements forged in our universe, the carbon, oxygen, and iron produced by our stars, could serve as the seed capital for the next. This would ensure a form of continuity across cosmic generations, a transfer of assets from a mature, defunct market to a new, emerging one. Just as dying stars scatter the ingredients for new stars to form, universes themselves might undergo a similar rhythm of collapse, rebirth, and renewal. Though it remains firmly in the realm of theory, this concept offers a vision where starlight never truly ceases. Instead, it shifts across scales larger than we can easily imagine, an eternal dance of economic collapse and revitalization. In this view, the stars above are not just part of our universe's story, but part of a pattern that could repeat endlessly. But before any potential end, there is the long, slow decline. This future will be dominated by the most successful and yet most overlooked stellar entities in the cosmos, the red dwarfs. Not all stars live the fast, violent lives of the hypergiants. The smallest ones, the red dwarfs, operate on a strategy of extreme efficiency and longevity. They burn their nuclear fuel so slowly, sipping their hydrogen with such patience, that they can shine for trillions of years, a timescale far longer than the current age of the universe. These stars are dim and cool, often invisible to the naked eye, but they are the silent majority. By sheer numbers, they are by far the most common stars in the cosmos, making up the vast majority of suns in the Milky Way. They are the bedrock of the galactic economy, the ultra-stable, long-term legacy institutions. Because they live so long, red dwarfs could host planets where life has an almost unimaginable amount of time to emerge and evolve. The fact that not a single red dwarf has yet reached old age is a critical piece of intelligence. The universe is still too young. That means the night sky of the far future will still be lit by these tiny, enduring embers long after brighter, more profligate stars like our Sun have vanished. As the cosmos ages, the strategic landscape will shift dramatically. The brightest, most massive stars, the market leaders of today, will burn out first. Blue giants and hypergiants last only millions of years. Stars like the Sun endure for billions, but the red dwarfs will persist for trillions. Over these immense timescales, they will become the only significant light sources in the universe. The galaxies of the distant future may glow only with their faint crimson light, a softer and lonelier sky. This is the red dwarf era, the cosmic twilight. It is a vision of a universe in a state of low energy stability, a final quiet phase of economic activity. Eventually, even these incredibly long-lived stars will exhaust their fuel, fading into white dwarfs and at last into the theoretical black dwarfs. The universe will shift from a bright, star-filled expanse to one lit only by the last dying embers of its most patient inhabitants. It is a vision of cosmic twilight where the final stars burn quietly, carrying the universe into its last chapters. For now, we live in its golden age, a brief, brilliant period of intense production, surrounded by magnificent suns of every size, color, and strategic disposition. Leaving the speculative deep future, our analysis returns to the high-stakes political realities of the present-day galaxy. At the centers of most major galaxies, including our own Milky Way, lurk the ultimate gravitational rulers, supermassive black holes, entities millions to billions of times heavier than the Sun. These are the seats of power, the imperial capitals around which the entire galactic economy revolves. And incredibly, some stars operate within their immediate sphere of influence, their existence a constant high-stakes dance with oblivion. In our own Milky Way, intelligence assets have been tracking the orbits of stars racing around Sagittarius A star, the 4 million solar mass black hole at our galactic core. These are the vassal states of the central power, bound in perilous orbits that serve as a constant demonstration of the black hole's absolute authority. One such star, designated S2, has become a key subject of our long-range surveillance. It follows a highly elliptical path that, at its closest approach, brings it within just 17 light hours of the black hole, a cosmic hair's breadth. At this point in its orbit, it accelerates to more than 5,000 kilometers per second, a staggering velocity forced upon it by the immense gravitational mandate of its ruler. To observe these orbits is the closest our analysts can get to direct espionage on a black hole. These vassal stars act as unwilling informants. By precisely tracking their paths, we can calculate the mass of the central black hole with extraordinary precision. More importantly, these orbits serve as the ultimate testing ground for our understanding of cosmic law. They trace paths through space-time so warped that they provide clear, undeniable confirmation of Einstein's predictions about how extreme gravity functions. These stars survive where we might expect them to be torn apart, proving that stable political arrangements, however precarious, can exist even in the shadow of an absolute power. Their continued existence is a testament to the fine line between being a subject and being a victim, a delicate ballet performed on the very edge of an infinite abyss. Their light, warped and stretched by their journey, carries with it the secrets of the central power, allowing us to study the nature of the beast without ever seeing it directly. However, a close encounter with the central power does not always result in a stable orbit of servitude. Sometimes the interaction is so violent that the star is not captured or destroyed, but exiled. In these chaotic gravitational exchanges, a star can be flung away at tremendous speeds, accelerated by the black hole in a powerful slingshot maneuver. These are the hypervelocity stars, the defectors and political exiles of the galaxy. They can be launched at millions of kilometers per hour, a velocity so great that it allows them to escape the gravitational pull of their home galaxy entirely. The Milky Way's own political history is written in the trajectories of several such runaway stars, which our sensors have tracked racing outward into the lonely intergalactic void. Their journeys likely began near Sagittarius A star, where a close pass with the central black hole acted as the catalyst for their permanent expulsion. For any planets that orbit such a star, the result would be an extraordinary fate, an entire solar system cast adrift, a population of worlds speeding alone through the cosmic dark. The discovery of these stellar exiles reveals a crucial aspect of galactic dynamics. The central power does not merely rule and consume, it is also an engine of chaos. It shapes its environment not only by what it holds close, but by what it violently hurls away. Our analysis of the galaxy often focuses on individual stellar actors, but intelligence reveals that solitude is not the default state of existence. To the naked eye, a star often appears as a single point of light, an isolated nation-state in the vastness of space. But in reality, a significant number of these are complex political alliances. Binary systems where two suns are locked in a gravitational pact are especially common. These are the galaxy's bilateral treaties. With two stars orbiting a shared center of mass, their destinies intertwined. Some of these pairs are so close their relationship is volatile, exchanging material like two nations engaged in fierce, unbalanced trade. Others are so distant they circle each other only once every thousands of years, a stable but remote alliance. In a world orbiting such a system, the sky would be a constant reminder of this complex relationship, with two suns rising and setting, casting multiple shadows. Our own nearest stellar neighbor, Alpha Centauri, is not a single entity, but a trilateral pact, a triple star system. By studying these intricate alliances, our analysts gain critical insight into the processes of star formation, the nation-building of the cosmos. The prevalence of these systems suggests that cooperation, or at least coexistence, is a fundamental strategy for stellar survival and evolution. Our Sun's solitary existence makes it less of a norm and more of an isolationist. This interconnectedness extends beyond the lives of stars and into their deaths. The end of one stellar empire can be the direct catalyst for the birth of new ones. When a massive star ends its life in a supernova, it does not simply vanish. The explosion creates a powerful shockwave, a wave of political and economic force that blasts through the surrounding interstellar medium. When this shockwave encounters nearby clouds of gas and dust, the undeveloped territories of the galaxy, it compresses them, triggering a new wave of star formation. This is the ultimate act of creative destruction. The violent death of one power directly funds and initiates the rise of the next generation. Our own sun may be a product of such a legacy. Intelligence suggests it was likely born from a nebula that was enriched and compressed by the shockwave from a previous, now long-dead stellar giant. This means the iron in our blood and the oxygen we breathe are the recycled assets of a fallen empire. This cycle of death and rebirth ensures that galaxies remain fertile zones of activity, continually recycling their capital into new forms. Every brilliant star that dies leaves behind more than just ashes. It leaves the seed funding and the economic stimulus for future suns, future planets, and perhaps future life. Stars do not simply end. They pass the torch, igniting the next chapter in the ongoing geopolitical story of the cosmos. While most stellar collapses are final, our surveillance has detected rare anomalies that defy this rule. In extremely unusual cases, a massive star may undergo a cataclysmic explosion, survive the blast, and then explode again years or even decades later. These bizarre events are known as pulsational pair instability supernovae. They are the resurgent empires of the cosmos, zombie states that refuse to accept their own demise. The star becomes so unstable that it violently erupts, ejecting huge amounts of its mass, but the core survives. It then stabilizes temporarily, a brief period of false recovery, only to later collapse for good in a final definitive detonation. These stars produce multiple bright outbursts that can confuse our analysts, making it appear as if multiple supernovae are occurring in the same location. These exotic stellar deaths highlight the dangerous diversity in the fates of the most massive stars. They are a profound intelligence challenge, revealing gaps in our understanding of nuclear physics and stellar instability. In cosmic terms, they are stars that seem unwilling to let go, their flickering death throes leaving a dramatic and confusing record of their struggle against gravity's final, inevitable pull. In the vast and chaotic theater of cosmic events, intelligence gathering depends on finding reliable signals amidst the noise. While some supernovae are rare and unpredictable, another class of stellar explosion is so consistent, so uniform, that it has become the bedrock of our strategic mapping of the universe. These are Type Ia supernovae, and they are the cosmic equivalent of a universal economic benchmark, a gold standard for measuring distance and value. They occur under a very specific set of regulated conditions. In a binary system, a white dwarf, the dense remnant of a dead star, accumulates matter from its companion. When the white dwarf's mass reaches a precise critical limit, it ignites in a runaway thermonuclear explosion. Because these explosions are always triggered at roughly the same mass, their peak brightness is nearly uniform across the entire universe. The overall mood of this reliable benchmark cannot be overstated. In the late 20th century, these standard candles played a pivotal role in one of the most profound and unsettling discoveries in the history of science. Our cosmological models, based on the known forces of gravity, predicted that the expansion of the universe should be slowing down. But when teams of astronomers used Type A supernovae to make precise measurements of distant galaxies, the data revealed something entirely different. The expansion was not slowing, it was accelerating. It was as if all our economic models predicted a market slowdown, but the most reliable indicators showed inexplicable runaway growth. This discovery pointed to a new and mysterious force at play on the largest scales, a dark energy that acts as a form of anti-gravity, pushing the universe apart at an ever-increasing rate. Type A supernovae, our trusted economic indicators, forced us to rewrite our entire understanding of the universe's ultimate fate. They are not only spectacular stellar deaths, but the fundamental yardsticks that revealed the existence of the most dominant and most mysterious force in the cosmos. Beyond their value as measurement tools, supernovae are the primary agents of wealth distribution in the galactic economy. Every atom of gold, silver, iron, and calcium on Earth was forged in the heart of a star. When massive stars explode, they blast these heavy elements into space, a final act of catastrophic generosity. This is the universe's foreign aid program, its system of economic reparations. The explosion enriches the interstellar medium, seeding vast territories with the high-value, manufactured materials necessary for future development. Over time, that material becomes part of new stars, new planets, and eventually living things. Without these violent acts of wealth redistribution, the universe would be a profoundly poor place, filled mostly with simple hydrogen and helium. Instead, every supernova sows the seeds of complexity. The iron flowing through your blood and the calcium strengthening your bones were once carried outward in such a blast, drifting through the void for eons before finding their way into the formation of Earth. Supernovae are violent endings, but they are also foundational beginnings. This leads to a conclusion that is not poetic, but a statement of literal scientific fact. You are made of stardust. The atoms in your body were forged in stars. The oxygen you breathe, the carbon that forms your cells, all were created in stellar cores and scattered by supernovae billions of years ago. The analyst Carl Sagan famously summarized this doctrine: "We are made of star stuff." The phrase captures a profound reality. Every human being, every living creature, every rock and tree is a collection of recycled stellar assets. We are the living embodiment of a cosmic supply chain that stretches across billions of years and unimaginable distances. When you look up at the night sky, you are not just gazing at distant suns. You are looking at the factories of your own origin. The stars provided the raw materials, and in turn, we are the universe becoming aware of itself. The link is direct, physical, and deeply humbling. A star's entire existence is governed by a single, ruthless economic principle. It must produce more energy than gravity consumes. For billions of years, it achieves this through nuclear fusion, a profitable enterprise of converting lighter elements into heavier ones. This process, a chain of ever more complex reactions, generates a net energy profit, but only up to a point. When the core of a massive star begins to fuse silicon into iron, the economic model fundamentally breaks. Iron is the poison pill of stellar economics. Fusing iron does not release energy, it consumes it. It is an unprofitable, energy-negative transaction. This means that once a critical mass of iron accumulates in a star's core, the fusion engine that supported the star against gravity for millions or billions of years is not just turned off, it is put into reverse. At that moment, a catastrophic collapse becomes inevitable. The presence of iron is a death sentence for a massive star, the cosmic tipping point that signals its economic and structural bankruptcy. It is a remarkable fact of cosmic industry that this ordinary metal, so fundamental to our own civilization, is also the element that guarantees the destruction of the universe's greatest giants. This catastrophic failure is best understood by examining the fundamental political dynamic that governs every star, a delicate balance between two powerful, opposing forces. On one side is gravity, the ultimate centralizing force, constantly pulling all of the star's mass inward, seeking to crush it into a single dense point.
On the other side is the outward pressure generated by nuclear fusion, an expansive, liberalizing force, pushing back against the crush of gravity with immense heat and radiation. As long as these two forces remain in a state of equilibrium, the star is stable.
This is the grand compromise, the hydrostatic equilibrium that allows a star to exist. Our own sun is a masterclass in this political stability, having maintained this perfect balance for over 4.5 billion years. And its strategic forecasts predict it will continue to do so for billions more. This constant tug-of-war is the fundamental reason stars exist as steady sources of light and energy, rather than either collapsing instantly or blowing themselves apart. They are monuments to a temporary, hard-won peace between the universe's most basic impulses. But this peace is fragile. The moment the fuel in the core runs out, or the moment the engine is poisoned by iron, the balance tips catastrophically and irrevocably. Without the outward push of energy from fusion, gravity's victory is not slow or gradual. It is absolute and instantaneous. The star implodes in mere moments, crushed by its own immense weight, in a collapse so rapid it triggers a violent rebound explosion, a supernova. The star's entire life, its billions of years of shining, was merely a temporary defiance of this single, inevitable outcome. Its light was not a passive glow, but the active, energetic signature of a desperate, ongoing battle. It was a fragile victory against the relentless inward pull of gravity. The final collapse is gravity's coup d'état, a hostile takeover that was always waiting patiently for the moment the star's defenses failed. Every star we see in the night sky is a warrior in this ancient conflict. Its light a testament to its current success in holding back the darkness of its own collapse. Not all stellar economies operate on the patient, multi-billion-year timeline of our Sun. In the grand strategic theater of the galaxy, there are nations that adopt a far more aggressive, high-growth, high-risk model. The most massive stars are the startup unicorns of the cosmos, consuming their nuclear fuel at astonishing rates, in some cases up to 1 million times faster than the Sun. This is a strategic doctrine of blitzscaling on a cosmic level. They possess immense capital in the form of hydrogen, but their burn rate is so ferocious that their lifespans are incredibly short, sometimes lasting only a few million years. By contrast, the Sun's strategic plan allows for roughly 10 billion years of stable operation. These fast-burning giants blaze with an intense blue light, pouring energy into space and fundamentally shaping their local galactic sectors with powerful radiation and stellar winds. They are the market makers, the disruptive innovators whose sheer output influences everything around them. However, their high-growth model is fundamentally unsustainable. Their short, spectacular lives invariably end in violence, typically in a catastrophic supernova that liquidates the entity entirely, but in the process enriches its sector with new, heavy elements. The contrast between them and stars like our Sun reveals a core principle of cosmic economics. Size and power dictate destiny. The bigger the star, the shorter and more dramatic its life cycle. They are cosmic fireworks, dazzling but fleeting, while smaller, more conservative economies like our Sun remain as steady candles across the deep expanse of time. This brings our analysis home to the long-term strategic forecast for our own Sun. Though it is a model of stability now, it has a programmed and dramatic future. In approximately 5 billion years, it will exhaust the primary hydrogen fuel in its core. The overall mood, some believe, will trigger a fundamental restructuring of its internal economy.
As fusion shifts from burning hydrogen to burning helium, the delicate balance of forces inside the star will be broken. The sun will swell enormously, transforming into a red giant. This is our star's final expansionist phase. Its surface will expand outward, its borders relentlessly pushing into the surrounding system. Our intelligence forecasts indicate it will certainly engulf Mercury and Venus. Its outer atmosphere may expand far enough to consume Earth as well. During this phase, the sun's outer layers will glow with a dim red light, far cooler than today's golden radiance, while its core contracts and heats to extreme temperatures. Eventually, this bloated empire will lose its coherence. The outer layers will drift away into space, forming a glowing, intricate structure known as a planetary nebula, a peaceful dissolution of assets back into the galactic commons. The core, the remnant of our once great star, will shrink and cool, becoming a white dwarf. Though this transformation is far in the future, it is a stark reminder that even the most stable systems are temporary. They follow life cycles written into the fundamental laws of physics, a predictable path of growth, maturity, and an inevitable transformative end. Our familiar life-giving star will one day become something entirely different. Having forecasted the distant future, our analysis now turns to the present strategic environment as seen from Earth. On any clear night, one stellar power dominates our local sector, Sirius. Also known as the Dog Star, it shines with nearly twice the brilliance of the next brightest star, Canopus. Its prominence in our sky is a function of two key strategic factors: significant intrinsic luminosity and, crucially, proximity. At only 8.5 light-years away, Sirius is one of our closest influential neighbors.
The overall mood and friendly tone. The overall mood is relaxed, engaging, and comfortable, perfect for bedtime reading and space narration. The tempo should be around 0.8. Its dominance is a constant reminder of our place in a populated galactic suburb. For millennia, ancient human civilizations recognized the strategic importance of Sirius, linking its appearance to agricultural calendars, mythology, and navigation. In ancient Egypt, its heliacal rising heralded the vital flooding of the Nile. But modern intelligence has revealed a critical fact hidden from the ancients. Sirius is not a monolithic power. It is a complex binary system, a close strategic alliance. The primary entity, Sirius A, is a hot, powerful main sequence star. Its companion, Sirius B, is a faint but incredibly dense white dwarf, the collapsed core of what was once a massive star itself. To the naked eye, they appear as one, a single piercing point of light. The Sirius system is a lesson in intelligence analysis. What appears to be a single, unified power is often a more complex coalition, a relationship between an active state and its legacy partner, bound together by gravity. This human impulse to map and name the heavens is as old as civilization itself. Long before telescopes provided detailed intelligence, ancient observers gave names to the brightest strategic assets they could see. These names were not arbitrary. They were carriers of meaning, tied to agriculture, mythology, and survival. Stars like Betelgeuse, Rigel, and Aldebaran trace their names to Arabic traditions of astronomy, a clear indicator of that culture's dominance in the field for centuries. Names like Vega and Altair derive from a mix of ancient Arabic and Latin roots. These names are a form of cultural treaty, connecting us to the very first strategic analysts who watched the same sky millennia ago in China, India, Greece, and Egypt.
While our modern astronomical agencies now use precise catalog numbers for operational clarity, these ancient names endure, echoing across time.
The overall mood with a warm, friendly tone. They are a reminder that our bond with the stars is not purely scientific. It is a deep cultural inheritance, a map of human history projected onto the cosmos. They represent the first human attempts to impose order on and claim understanding of the vast, intimidating strategic map of the night sky. This ancient understanding was not merely academic. It was a critical tool of exploration and empire building. Before the invention of compasses and GPS, the stars served as the first reliable global navigation network. Polynesian voyagers, the masters of celestial navigation, crossed the vast Pacific by memorizing the rising and setting points of hundreds of stars, steering their canoes across thousands of kilometers of open ocean with stunning precision. In the Northern Hemisphere, the North Star, Polaris, served as a fixed intelligence asset, a constant beacon in the sky from which any navigator could determine their latitude. Arab traders charting the Indian Ocean, Greek sailors expanding across the Mediterranean, and Viking explorers pushing into the North Atlantic all relied on this celestial map to guide their journeys. This was the era's most advanced strategic technology. The ability to read the stars was a significant military and economic advantage, allowing for the establishment of long-range trade routes and the projection of power across oceans. Long before technology gave us satellites, humanity trusted starlight to carry them safely to new lands and to build the first global economies. Humanity's strategic reliance on the stars was built on a foundational assumption that the heavens, while in motion, were fundamentally constant. The North Star, in particular, was the ultimate fixed asset, the unwavering navigational and political pole around which the entire sky revolved. But this, too, is an illusion of a short-term perspective. The Earth's axis is not stable. The overall mood of this long-term cycle, known as precession, this means the celestial pole shifts, and the title of North Star is a temporary political appointment. Our current North Star, Polaris, has not always held this crucial role, and it will not hold it forever. Our intelligence on this long-term cycle is clear. Around 3000 BCE, during the height of ancient Egypt, the pole was marked by the star Thuban in the constellation Draco. Ancient monuments, like some of the Great Pyramids, were aligned to this former celestial hegemon. Looking forward, our strategic forecasts show that in about 12,000 years, the bright star Vega will assume the title. Polaris is merely the current chapter in a long story of shifting celestial power. To watch the pole star change is to witness the deep, slow breathing of the Earth itself, a powerful reminder that even the patterns we trust as absolute are always in flux. This relativity of perspective is not just a function of time, but of space. If you could stand on a planet orbiting a distant star, the familiar constellations, the strategic maps of our night sky, would vanish entirely. The groupings of stars we recognize are an optical illusion, a subjective interpretation based on our unique vantage point within the Milky Way. Seen from even a few dozen light-years away, their three-dimensional arrangements would warp into unfamiliar patterns. The great powers and alliances we see are purely a matter of our local perspective. From a planet orbiting our nearest neighbor, Proxima Centauri, our own sun, the center of our universe, the source of all our life and power, would appear as just another moderately bright star in their sky, perhaps part of a constellation completely unknown to us. From the Andromeda Galaxy, the entire Milky Way would be a single glowing band, and every star we hold as a landmark would be lost in its collective swirl. This is a humbling lesson in strategic intelligence. Your map of the universe is not the map. It is simply your map. To imagine other skies is to realize how deeply our view of the cosmos is shaped by the precise and ultimately arbitrary location from which we observe it. Combining these two principles leads to an inevitable conclusion. The entire strategic map of our sky is temporary. The constellations we know, Orion the Hunter, Cassiopeia the Queen, the Big Dipper, are fleeting arrangements. The stars themselves are in constant, independent motion, drifting through the galaxy on their own trajectories. Over thousands and millions of years, these slow, almost imperceptible movements will add up. The familiar patterns will warp beyond recognition. The three stars of Orion's belt will drift apart. The handle of the Big Dipper will break, and entirely new groupings, new alliances will emerge from the chaos. To us, these changes are too slow to notice in a single lifetime. But on the timescales of civilizations, the sky is ever-changing. Future human civilizations, or perhaps other species, will inherit skies filled with different maps. They will project their own myths, their own politics, onto new patterns of stars. The constellations we see tonight are merely a snapshot of a fleeting alignment, a powerful reminder that nothing in the cosmos is permanent, not even the borders we draw between the stars. Our perception of the cosmos is limited by the power of our instruments and the fundamental laws of light. But the universe itself contains a hidden tool for intelligence gathering, a phenomenon predicted by Einstein and confirmed a century ago. Gravity bends light. When the light from a distant star passes near a massive object, such as a galaxy or a black hole, its path is warped and magnified. This is gravitational lensing, and it is the universe's own signals intelligence program. In this scenario, the massive foreground object acts as a natural telescope, a cosmic listening post that intercepts and amplifies faint signals from the deep background. This can split a single star's light into multiple distinct images, allowing our analysts to cross-verify the signal. In other cases, it can make a star appear far brighter than it truly is, momentarily bringing a target that is beyond our normal observational range into sharp focus. Using this technique, our agencies have observed individual stars across billions of light years, targets that would otherwise be completely invisible. This is nature's magnifying glass, a fundamental tool of cosmic espionage that allows us to peer farther into the universe's past than our technology alone could ever manage. It shows us that space is not empty, but a flexible medium whose contours can be exploited to reveal hidden treasures. This ability to see across deep time confirms the long-term forecasts of cosmic change. The familiar patterns in our sky, the constellations that have guided humanity for its entire history, are temporary political blocks. As the Milky Way rotates and its constituent stars drift on their own paths, these historic alliances will dissolve. Our models are clear. In about 50,000 years, the recognizable form of Orion will be gone, its bright stars having scattered across the sky, their treaty of mutual alliances broken. In a few million years, the Big Dipper will no longer resemble a dipper at all. To future observers, these constellations, so fundamental to our own celestial map, may not exist in any recognizable way. Just as ancient humans saw different pole stars than we do, future beings will inherit their own sky, with their own alliances and their own myths tied to a passing arrangement of stars. They remind us that the sky itself has a history, and the strategic maps we make of it will someday be as outdated as old charts of the seas. The hard data underpinning these forecasts comes from the painstaking work of tracking proper motion. Though they appear fixed to the naked eye, all stars are in constant motion, and their immense distances simply make this movement nearly invisible. But over centuries and millennia, the changes accumulate. This gradual drift across our line of sight is proper motion, and for our analysts, it is the equivalent of tracking troop movements on a galactic scale. Barnard's star, for example, is a high-velocity target, shifting its position against the background stars so quickly that the change is noticeable every few decades. By comparing ancient star maps, the first intelligence reports from our ancestors, to our modern high-precision charts, we can reveal the slow, relentless shuffle of the heavens. Even the shapes of the constellations have subtly changed over the course of recorded human history. This shifting sky is the ultimate proof that what seems eternal is not. The stars are not fixed points on a celestial sphere. They are individual suns, traveling on independent trajectories through the galaxy, their light tracing lines of motion across cosmic time. The slow drift of the stars is not a random shuffle. It is part of a grand, coordinated motion, a galactic rotation in which our own sun is a willing participant. Our star is not a fixed entity. It is a nomadic nation on an epic journey, orbiting the center of the Milky Way once every 200 million years. This means that our entire local strategic environment is temporary. The stars that are our neighbors today will drift away, replaced by others as we cross their galactic paths. In the distant past, when dinosaurs walked the Earth, the Sun's closest stellar neighbors were entirely different. The night sky was populated by a different set of local powers. As our Sun continues its grand journey, the constellations we know will not only warp due to proper motion, but will be fundamentally replaced by new neighboring stars. This cosmic motion shows that even our star's position in the galaxy is transient, part of a grand rotation carrying us through different sectors, different political climates, and different neighborhoods across the ages. The sky above is just one frame in an endless journey. While our Sun navigates the dynamic, modern spiral arms of the galaxy, other, far older societies exist in self-imposed isolation. Orbiting the galactic periphery are the globular clusters, dense spherical swarms of stars that are the ancient, isolated civilizations of the cosmos. These are living fossils. Each cluster can contain hundreds of thousands of stars, packed into a relatively small space, bound by their own collective gravity. Many of these clusters in the Milky Way are more than 12 billion years old, nearly as ancient as the universe itself. They are the remnants of the galaxy's founding era. Their populations consist almost entirely of small, faint red dwarfs and other long-lived giants. Their more massive, influential stars burned out and died eons ago. Viewed through a telescope, a globular cluster is a dazzling snowball of light, a fortress nation that has preserved its original population and culture, untouched by the chaotic politics of the galactic disk. These clusters are more than just beautiful relics. They are windows into the past, invaluable historical archives that show us how the first stars formed and lived. Studying them is like reading a history book written in starlight. Beyond these isolated citadels, there are other survivors from the dawn of time, even more rare and valuable from an intelligence perspective. Hidden among the younger generations of stars within our own galactic neighborhood are a few clandestine elders, ancient suns that date back almost to the Big Bang. These are the sleeper agents of the cosmos. Some are more than 13 billion years old. They formed from primordial gas containing almost none of the heavy elements produced by later stellar generations. Our analysts identify them by studying their spectra, the chemical fingerprints in their light. A lack of heavy metals is the telltale sign of their ancient origin.
an economic signature of a time before the universe had been industrialized by supernovae. Such ancient stars are incredibly rare, but they offer direct clues about the first moments of star formation, before the galactic economy was flooded with new capital. To gaze upon one is to look into deep time, connecting with a survivor from an era when the universe was still young, dark, and just beginning to sparkle with the first light of creation. They are the hidden relics that allow us to verify our models of the universe's origin.
The identity of a star is tied to its home galaxy, but that citizenship is not always permanent. Galaxies themselves are dynamic political entities. They collide, they merge, and sometimes they are torn apart by gravitational forces. Yet, the individual stars within them can outlast these grand transformations. A star born in a small dwarf galaxy, a minor nation-state, might find itself swept up and integrated into a vast spiral galaxy like our own after a galactic merger. It becomes a new citizen of a greater empire, continuing to shine for billions of years, its origins betraying a now defunct political entity. In other, more violent scenarios, stars can be flung into intergalactic space as their home galaxy dissolves entirely. They become stateless refugees, wandering alone long after their nation has ceased to exist. In this way, stars can survive events that erase the very structures that created them. It is a profound reminder that stars are both products of galaxies and independent entities, capable of carrying on long after galactic borders are redrawn. These lone survivors are cosmic witnesses, their light a living testimony to the upheaval and political history of the cosmos, their chemical composition the only remaining record of their lost homelands. While some stars carry the history of dead galaxies, others wear the history of their own internal turmoil as a visible shroud. Our intelligence has revealed that some stars are cloaked in mysterious shells of gas and dust, material ejected from their surfaces during periods of extreme instability. These shells can form glowing rings, intricate arcs, or vast bubbles, all illuminated by the star's own radiation. These are the visible scars of recent upheaval. The causes vary. Some stars lose mass through powerful but steady stellar winds, a controlled release of assets. Others undergo violent eruptions that briefly swell their borders and shed their outer layers in a sudden, chaotic event. This ejected material often becomes part of a beautiful and complex nebula, a monument to the star's turbulent past. In some cases, our long-range imagery reveals multiple concentric shells, suggesting a star has undergone repeated episodes of crisis and recovery. These gas shells are not merely decorative. They are active contributions to the galactic economy, enriching the interstellar medium with elements that will one day form new stars and planets. To study them is to catch a star in the act of transformation, a celestial body wearing its own dramatic history in glowing veils for all to see. This process of mass shedding reaches its most violent and productive peak in a rare class of object known as a Wolf-Rayet star. These are the end-stage industrialists of the cosmos, massive, incredibly unstable, and nearing the end of their lives. They burn so hot and so bright that their outer layers are violently blown away in fierce, relentless stellar winds. These winds can strip away more than 10 Earth masses of material every single year. This is a frantic end-of-life liquidation of assets. Their exposed cores, stripped of their outer layers, glow with searing heat, often reaching temperatures above 50,000 degrees Celsius.
Wolf-Rayet stars are in a brief transitional stage before their final inevitable collapse, either as a supernova or into a black hole. Despite their extreme rarity, they play an outsized role in the galactic economy, furiously enriching their local sectors with the heavy elements forged deep within their cores. Their turbulent winds and eventual explosions scatter the high-value raw ingredients for new worlds.
The overall mood is not always a static broadcast of light and heat. For some, it is a dynamic, kinetic force projected onto their surroundings. When a star races through the interstellar medium at high speeds, it plows into the ambient gas and dust, creating a bow shock in front of it, much like the wake of a boat moving through water. This is the star's forward vanguard, a visible shock front announcing its arrival. These bow shocks glow in infrared light, where our surveillance assets can spot them as distinct arcs or crescents preceding the star. This is a valuable intelligence signal, revealing both the velocity and trajectory of the star, as well as the economic conditions, the density, of the territory it is moving through. These stars are often the runaways, the exiles we have previously identified, and their bow shocks are the luminous footprints marking their restless and lonely journeys across the galaxy. They are not passive travelers, they are active agents of disruption. Their passage compresses and energizes the regions they invade. These runaway stars streak across the galaxy like cosmic exiles, their very existence a testament to the chaotic side of the universe. Launched by the explosive kick of a supernova or the gravitational slingshot of a supermassive black hole, their lives are defined by their violent origins. They are the rogue operatives, the fleets cast out from their home nations, now operating in the vast, unclaimed territories of the galaxy. The implications for any planetary systems they possess are profound. A natural male narrator, potentially harboring life, hurled alone into the cosmic wilderness, forever severed from the gravitational and social fabric of its home galaxy. This is the ultimate political exile, a journey into a permanent and silent diaspora. The existence of these high-speed exiles is a reminder that even stellar mass entities are not immune to the unpredictable outcomes of gravity's great games, where the roll of the dice can send an entire solar system into oblivion. While the runaways are a story of high-speed, visible drama, the birth of a star is a clandestine affair. Newborn stars rarely reveal themselves right away. They are developed in secret inside thick clouds of gas and dust, the remnants of the raw material that collapsed to form them. These dusty cocoons are a form of natural stealth technology, blocking all visible light and hiding the nascent stars from conventional observation. To penetrate this veil, our agencies must deploy specialized surveillance assets. Using infrared and radio telescopes, our analysts can peer through the dust, revealing clusters of protostars still in their classified formative stages. These are embryonic nations, quietly gathering mass and influence before their public debut. Often, these young stars are surrounded by swirling disks of material, the initial infrastructure projects that may one day form planets. In time, the star's own radiation and stellar winds, its first broadcast of power, will clear away the surrounding dust. This is the star's coming out party, the moment it emerges from seclusion and announces its sovereignty to the galaxy. To catch a glimpse of a newborn star is to witness creation in progress, a rare and delicate stage of clandestine development that decides the future of an entire system. A star's entry onto the galactic stage is not instantaneous. Before its main economic engine of nuclear fusion ignites, it exists in a prolonged formative phase as a protostar. During this period, which can last for hundreds of thousands of years, the star is a pre-industrial nation, its economy running on a primitive and inefficient power source.
It glows not with the fire of fusion, but with the raw heat generated by its own gravitational collapse. This is the era of primordial capital accumulation. The protostar actively gathers material from its surrounding nebula, its gravity pulling in gas and dust, growing larger, denser, and hotter. This process is often violent and unstable. Powerful jets of gas, known as Herbig-Haro objects, frequently stream from the protostar's poles. These are the inefficient byproducts of a chaotic and rapidly developing system, a young state violently expelling energy and material as it struggles to achieve equilibrium. This entire hidden phase is the universe's quiet prelude to starlight, the period when the future of a sun is still being assembled from darkness and chaos. The transition from this primitive state to a modern industrial power is marked by a single critical event: ignition. Only when the protostar has accumulated enough mass and the pressure and temperature in its core reach a phenomenal 10 million degrees Celsius does hydrogen fusion begin. This is the star's industrial revolution. The moment its primary economic engine comes online, it officially becomes a star, a self-sustaining entity capable of balancing its own gravitational pressures for billions of years. It marks its graduation from a developing body into a stable, long-term player in the galactic community of nations. This ignition is the defining moment that separates the successful from the unsuccessful, the moment a protostar either achieves its destiny or falls short, for not every developing body makes it.
The universe is littered with failed states. In the twilight zone between planets and stars exist the brown dwarfs. These objects are the tragic figures of cosmic development. They are too massive to be classified as planets, but they were ultimately unsuccessful in accumulating enough capital to ignite sustained hydrogen fusion in their cores. They are the stellar nations that collapsed into a permanent state of economic recession before ever achieving industrialization. They glow faintly, not with the power of a stable economy, but with the residual heat from their formation, a pale imitation of a true star. Some may briefly fuse deuterium, a heavier form of hydrogen, but this is a temporary, low-yield activity that quickly fades. Our analysts classify them as failed stars or, conversely, overgrown planets. They are a stark reminder that the universe has little tolerance for falling short of critical thresholds. They challenge our neat categories, demonstrating that the cosmos often produces entities that exist in a state of perpetual incompletion, a powerful lesson that not every attempt at creation is a success. The life of a star is not always a solitary journey. The universe is rife with complex interstate relationships, from stable alliances to outright mergers. When two stars in a binary system orbit close enough, their gravitational destinies can intertwine, leading them to spiral together and merge into a single, larger entity. This is the cosmic equivalent of a corporate merger or a state unification. Such collisions release enormous amounts of energy, producing spectacular outbursts that serve as the public announcement of the merger. The resulting star is often larger, hotter, and more unstable, its internal economy now burning through new layers of nuclear fuel. The overall mood of stars are not isolated, but are constantly being reshaped by chance encounters and the relentless pull of gravity. However, not all close relationships are mergers of equals. In many binary systems, the dynamic is far more predatory. Here, one star grows at the direct expense of its companion in a process of cosmic vampirism. As one star in the alliance ages and expands into a giant, its outer layers, now weakly held by gravity, can spill over onto the other star. This is mass transfer, a relentless siphoning of resources from one state to another.
This act of predatory economics dramatically alters the destinies of both stars. The receiving star, the predator, may grow hotter and brighter, its life extended and revitalized by the stolen assets. The donor star, the victim, is stripped down to its core, its outer layers cannibalized, often leaving behind the husk of a white dwarf. This is a relationship of cosmic thieves and victims, their lives bound together in a partnership as complex and destructive as any myth, played out in light and fire across millions of years. The strategic consequences of this resource siphoning can be catastrophic. In some scenarios, the stolen material piling on to the surface of a white dwarf can trigger a runaway thermonuclear event, a nova, causing the star to briefly flare with incredible brightness.
The overall most dramatic and powerful phenomena in the sky, from flickering variable stars to system-destroying explosions. They are a stark lesson in cosmic geopolitics. Close alliances can be sources of immense instability, and an unchecked imbalance of trade can lead to the utter destruction of one or even both partners in the pact. The sky is a laboratory for every model of interstate relations, from cooperation to predation. Beyond the straightforward dynamics of binary systems lie even more complex political structures. Some stars form into trilateral pacts, orbiting in delicate and often chaotic gravitational dances. These triple star systems can be arranged in several ways, but a common model is a close binary pair with a third star orbiting the pair from a greater distance. This is the celestial equivalent of a federation, with a tightly integrated inner power block and a more loosely associated third member. These systems can generate chaotic gravitational effects, a profound political instability that influences the motion of any smaller bodies, such as planets, caught within their domain. A planet in such a system would experience a bewildering reality, its seasons and daylight governed by the shifting allegiances and gravitational whims of three separate suns. These complex federations demonstrate that the universe's political arrangements are not always simple, showcasing a preference for variety and complexity that often leads to instability. For a long time, science fiction speculated about worlds with two suns, but our intelligence has now confirmed them as a reality. Planets can and do exist in stable orbits around binary stars, a state of cosmic joint sovereignty. In such systems, a planet would be a nation governed by a joint ruling council. It would experience complex daylight cycles with twin sunsets and shifting patterns of light and shadow. NASA's Kepler telescope has discovered several such circumbinary planets, proving these exotic arrangements are not just theoretical, but are a viable model for planetary systems. Life under multiple suns would be shaped by cycles utterly alien to us on Earth. Seasons, light levels, and even the fundamental rhythms of biology could behave in unpredictable ways, all dictated by the intricate gravitational relationship of the two parent stars. These systems fundamentally expand our understanding of what is possible, reminding us that the diversity of planetary environments is far wider than our single sun-centric imagination once allowed. They are proof that stable nations can form and persist under the authority of even the most complex ruling coalitions. This impulse toward community exists on even grander scales. Not all stars are born in small families. Some are born in vast star clusters, sprawling stellar metropolises that can host hundreds of thousands of suns. We have discussed the globular clusters, the ancient fortress-like capitals that preserve the galaxy's early history. But there are also open clusters, which are younger, looser, and more transient. These are the booming industrial parks of the galaxy, often blazing with the light of hot, massive young blue stars. Over hundreds of millions of years, however, these loose associations are gradually pulled apart by the gravitational tides of the galaxy.
Eventually, their member stars disperse, leaving the city of their birth to join the general galactic population. They are not born alone, but as siblings, companions for a brief cosmic period before scattering to live out their separate fates. This process of urban dispersal is fundamental to the story of our own existence. Our sun, now a solitary star navigating the galactic suburbs, is believed to have been born in just such an open cluster, approximately 4.5 billion years ago. Its sibling stars, the companions of its youth, have long since drifted away, now scattered across the Milky Way, their familial connection lost to time. Our star is a migrant from a now dissolved stellar metropolis, a citizen that has long since left its crowded hometown. To look into an open cluster like the Pleiades is to get a glimpse of the kind of chaotic, brilliant, and crowded stellar nursery that our own sun once called home. It is a profound connection to our origins, a reminder that even our stable, solitary star was once part of a great temporary community, its destiny forged in a brilliant city of light that no longer exists.